Exceptions or violations of Kuchbek equation. Case here. If mechanism consists of sliding pairs only, delta SY, delta SX 1 or 2, 3, and P13, P23, P1, comma 2. N is equal to 3, J is equal to 3, H is equal to 0. Degrees of freedom is equal to 3 into 3 minus 1 minus 2 into 3 minus 0 is equal to 6 minus 6 is equal to 0. According to Kuchbek equation, it is a structure. But delta Sy of link 3 is equal to function of delta Sx of link 2, output pair variable, input pair variable. Actual degrees of freedom is equal to 1. Minimum 3 links are required to obtain a constraint mechanism having sliding pair only or lower pair surface contact. Case 2. If a mechanism consists of redundant parameters, links, pairs, mobility of any link. Modified Kuchbek equation, degrees of freedom is equal to 3 into n minus nr minus 1 minus 2 into j minus jr minus h minus fr. N is equal to total number of links, j is equal to total number of lower pairs, h is equal to total number of higher pairs. NR is equal to number of redundant links and JR is equal to number of redundant lower pairs. FR is equal to number of redundant degrees of freedom. These are just questions from workbook. The parameters whose presence and or absence does not affect the mobility of any linkage is known as resonant parameter. Is known as redundant parameter. Example: double parallelogram linkage to connect a wheel in locomotives. Circle A, B, C, D. These CD and AB are parallel at all points. AB is equal to CD, AB is parallel to CD, AD is equal to BC, and AD is parallel to BC. These BC and AD are also parallel. Degrees of freedom is equal to 1. Interference uncertainty configuration. Locus of B circle, locus of C circle. Center A radius is equal to AB, center D radius CD. BC parallel to B1 C1, parallel to B2 C2, parallel to B dash C dash. Corresponding uncertainty configuration: when all the links of parallelogram becomes collinear, the rigidity of mechanism becomes minimum, hence the chances of failure becomes maximum. In order to increase rigidity without affecting the mobility, extra link needs to be connected to some link. Here, when all these A, B, C, D are in a straight line, like uncertainty configuration, when all links are becomes collinear, rigidity of mechanism becomes minimum, chances of failure maximum. So some link has to be connected in between, either coupler, either AB parallel to EF parallel to DC, one EF link is double parallelogram linkage, or E, or this linkage in this represented in this way or in this way. EF coupler, EF parallel to AD parallel to EF parallel to BC. AD parallel to BC. If EF present or not, degrees of freedom is equal to 1. EF acts as redundant link. N is equal to 5, J is equal to 6, H is equal to 0, as 6 revolute pairs are there. According to Kuchbek equation, degrees of freedom is equal to 3 into n minus 1 minus 2j minus h is equal to 3 into 5 minus 1 minus 2 into 6 minus 0 is equal to 12 minus 12. According to Kuchbek equation, double parallelogram linkage is a structure, but actual degrees of freedom is equal to 1. That is, degrees of freedom, that is, double parallelogram is violating Kuchbek equation. Modified Kuchbek equation, degrees of freedom is equal to 3 into n minus nr minus 2 into j minus jr minus h minus fr. And this NR is equal to 1, JR is equal to 2. So degrees of freedom 9 minus 8 is equal to 1. Uh, uh, FR is equal to 0. Double parallelogram linkage or EM linkage is a constrained mechanism. If any link parallel to EF are connected also, for that also FR is equal to 0, degrees of freedom is equal to 1. Here these three are parallel. If you calculate, degrees of freedom is equal to 1. If one link is connected which is not parallel, then degrees of freedom is equal to 0, omega 4 is equal to 0. As there is no output, link 5 is restricting the forward motion. 5 is not a redundant link, that is, if link 5 is not present, degrees of freedom is equal to 1. As this is there, as link 5 is there, degrees of freedom is equal to 0. Example way, oscillating cam and follower mechanism. Coupler delta pi delta theta is output. N is equal to 4, 1 2 3 4, 1 2 3 4 links. J is equal to 3, 1 2 3. H is equal to 1. Degrees of freedom is equal to 3 into n minus 1 minus 2j minus h is equal to 3 into 3 minus 2 into 3 minus 1 is equal to 9 minus 7 is equal to 2. According to Kutzbach's equation, it is an unconstrained mechanism. One input will result in two output. But delta pi is a function of f of delta theta. Delta pi is function of delta theta. Input output pair variable, input pair variable. Actual degree of freedom is equal to 1. Explanation: redundant pair. Let R12 R12 B is redundant pair. Remove R12, fix cam, then the degrees of freedom is 0. Therefore R12 is not redundant pair. Let R14 be redundant pair. Remove R14 and fix 4. The degrees of freedom is 0. R14 is a not redundant pair. Fix R34 here. This is only for visualization purpose. Don't do calculations based on this rough diagram. Okay, degrees of freedom equal to 1. Either we can take NR is equal to 1, JR is equal to 1, FR is equal to 0. Modified Kutzbach equation. 3 into 4 minus 1 minus 1 minus 2 into 3 minus 1 minus 1 minus 0 is equal to 6 minus 4 minus 1 is degrees of freedom is equal to 1. Kinematic chain. R34 pair permits rolling between cam and follower. If it is absent, there will be sliding in which friction will be more. The only purpose of R34 is to reduce friction and not affect the mobility. Hence it can be considered as redundant parameter. Explanation: redundant degrees of freedom. Modified Kutzbach equation, degrees of freedom is equal to 3 into 4 minus 0 minus 1 minus 2 into 3 minus 0 minus 1 minus 1. FR can be considered as 1. Then 9 minus 6 minus 2, degrees of freedom is equal to 1. FR equal to 1, spinning of roller, and we will consider NR is equal to 0 or JR is equal to 0. Either in this way or above way. Only example having two explanations. Spinning of roller does not affect mobility. Fr is equal to 0 in this respective example due to spring action between cam and follower at contact. Example C, 1 2 3 4, n is equal to 4, j is equal to 1 2. Here sliding pair, here sliding pair. 4 j is equal to 4, h is equal to 0. Without rotation also bar will slide outside. According to Kutzbach equation, degrees of freedom is equal to 1, but link 3 can slide out of 2 and 4, hence actual degrees of freedom is equal to 0. Modified Kutzbach equation, n is equal to 4, j is equal to 4, h is equal to 0, nr is equal to 0, jr is equal to 0, fr is equal to 1. FR is equal to 1. Degrees of freedom is equal to degrees of freedom is equal to 3 into 4 minus 0 minus 1 minus 2 into 4 minus 0 minus 0 minus 1 is equal to 0. If we use instead of round bar square bar, by observation only we can describe degrees of freedom is equal to 0, but mathematically not possible. That is only one pair variable. If curve bar, then degrees of freedom is equal to 1, and this we can't describe by observation if motion is present or not. If caps are used on both sides, degrees of freedom equal to then on both sides the degrees of freedom is equal to 1. Range of movement of input and output links in simple planar mechanism. The dimensions of links plays an important role in range of movement. According to the Grashoff's law, in order to obtain continuous rotation between two links in a simple planar mechanism, the sum of shortest and longest link should not be greater than sum of other two links. This is Grashoff's law. On basis of input and output, 4-bar mechanisms can be for the following types: crank or double crank or drag link mechanism, crank rocker mechanism, rocker crank, rocker or double rocker mechanism. Note: crank, the link which is able to execute full circular motion, that is rotation. Rocker, the link which can oscillate on basis of relation between sum of shortest link length and longest link length with respect to other two links lengths. Simple planar mechanism are being divided in three classes. Class 1 linkage, Grashof linkage. Condition: Lmin plus Lmax less than P plus Q. Lmin length of shortest link, Lmax length of longest link, P plus Q length of other two links. Lmin plus Lmax less than P plus Q for a Grashof law. Inversion of class 1 linkage: the position of shortest link, that is Lmin, determines the type of inversion in class 1 linkage. Inversion 1: if Lmin is fixed, crank mechanism. If inversion 2: if Lmin is adjacent to fixed, then crank rocker or rocker crank mechanism, Lmin will become crank. This will be crank. Okay. Inversion 3: Lmin is coupler, rocker mechanism. Class 2 linkage or non-Grashof linkage. Condition: Lmin plus Lmax greater than P plus Q. All the inversions of class 2 linkage will be double rocker mechanism. Class 3 linkage or transition linkage. Condition: Lmin plus Lmax is equal to P plus Q. Special Grashof's linkage. The inversions of class 3 linkage are similar to that of class 1 linkage. It is also known as special Grashoff's linkage. Lmin plus Lmax is equal to P plus Q. If all links are of equal length, Lmin is equal to Lmax is equal to P is equal to Q, then crank rhombus linkage. If two links are of equal length, Lmin is equal to P, Lmax is equal to P. Equal length links are opposite to each other. Parallelogram linkage, double crank. Equivalent links are adjacent to each other. Deltoid or kite linkage. If Lmin is fixed, then gallow linkage is crank. If Lmax is fixed, crank rocker. If summation of Lmin and Lmax is not greater than other two links, minimum one crank will be always there. That is class 1 and class 3. Minimum one link will be able to execute full circular motion. In rocker mechanism, coupler will execute full circular motion and becomes crank. Inversion of a mechanism cannot affect the ability to transfer relative motion. Inversion can affect the type of relative motion, that is absolute motion of any link. Grashoff's linkage Lmin plus Lmax less than or equal to P plus Q. First class linkage Lmin plus Lmax less than P plus Q. Equivalent linkages springs 1 or 2, 3 and connected by spring 2 linkages and 1 revolute. On the spring is equal to 2 kinematic links. N is equal to 3, J is equal to 2, 1, J is equal to 2, J is equal to 2, H is equal to 1. This and this and this. Degrees of freedom is equal to 3 into 3 minus 1 minus 2 into 2 minus 1 is equal to 6 minus 4 minus 1 is equal to 1. If the spring is replaced by 2 links with 1 revolute pair, N is equal to 5, J is equal to 4 revolute plus 1 prismatic is equal to 5, H is equal to 1. From this also we will get degrees of freedom is equal to 1. Higher pair. RA is equal to RB, N is equal to 3, J is equal to 2, H is equal to 1, crank mechanism. This can be a parallelogram link replaced by parallelogram linkage. Anti-parallelogram linkage is like this. We see 1 or 2. One higher pair is equal to 1 kinematic link plus 2 lower pair. 1 kinematic link and 2 lower pair like this and this. Based on options, 1 higher pair is almost equivalent to 2 lower pair. Based on options. Single slider mechanism. L A B C D. L A is equal to circle locus of a point. L C is equal to arc of circle center D, the radius DC. If LDC tends to infinity, LC tends to straight line. By making two lengths infinity, we are getting single slider mechanism. Those two links are LDC tends to infinity, LAD, that is fixed link is also turning to infinity. A, B, C. There are two types: E, eccentric, and on the line only single slider mechanism. Double slider mechanism, if LAB tends to infinity, LB tends to infinity. By making three links infinite length, we are getting double slider mechanism. LAB tends to infinity, LDC tends to infinity, LAD tends to infinity. Inversion of single slider mechanism. 1 or 2, 3, 4 slider crank connecting rods. Lmax plus Lmin. Lmax plus Lmin P plus Q. Like Lmax is infinity and Q is infinity. LH is almost equal to RHS. Class 3 linkage. Inversion 1 if link 1 is fixed. Crank rocker mechanism. Applications offset slider crank quick return mechanism, QRM crank rocker, and reciprocating IC engine rocker and reciprocating compressor. Reciprocating IC engine rocker crank, reciprocating compressor crank rocker. Inversion 2 link 2 is fixed, that is crank is fixed. Application crank mechanism. Application Whitworth QRM or Whitworth QRM quick return mechanism, radial engine or star engine. RNL line of stroke of cylinder 1, line of stroke of cylinder 2. Inversion 2 if link 3, that is connecting rod is fixed. If link 3, that is connecting rod is fixed. Crank rocker mechanism. Application oscillating cylinder engine mechanism. Crank rocker oscillating cylinder engine mechanism. Crank and slotted bar QRM crank rocker. Inversion 4, the link 4, that is slider is fixed. Rocker mechanism, hand pump, rocker plunger mechanism. Inversions of double slider mechanism, Lman plus Lmax, P plus Q, this is side infinity, this side infinity plus infinity, class 3 linkage. Slider coupling rod, slotted bar. Inversion 1, that is slotted bar is fixed. Slotted bar is fixed. AB point on P on rod P x P yp is equal to AP sin theta, x is equal to BP sin theta, cos square plus sin square theta is equal to 1, xp square by BP square plus yp square by AP square is equal to 1. Locus of P, let AP greater than BP, ellipse semi major axis is equal to AP, semi minor axis is equal to BP, central is equal to 0, 0, rocker elliptical trammel. Special cases, if P is midpoint of link AB, AP is equal to BP, XP square plus YP square is equal to AP square is equal to PP square. P is circle, its center 0, 0, radius AP is equal to BP. If P exists on any one of slider, LP is equal to straight line. Inversion 2, if either link 2 or link 4, that is slider is fixed. Displacement of slotted bar x is equal to P1 A1 is equal to OA1 minus OP is equal to OA minus OA cos theta. X is equal to OA into 1 minus cos theta. Displacement of slotted bar is SHM in nature. X is equal to OA into 1 minus cos theta. Crank rocker mechanism used to generate sine functions. Scotch-Yoke mechanism, rotation to SHM. Inversion 3, link 3, that is coupling rod is fixed. Crank mechanism, application old arms coupling, input shaft, output shaft, horizontal coupling, vertical coupling. Velocity ratio 1 by 20 to 1 by 50, 1 by 100. Higher velocity ratio. Worm and worm wheel. Worm rotates, worm wheel. Worm wheel. Reverse is not possible. Worm rotates, worm wheel. Shafts are parallel, gear and pinion. Shafts are parallel and away. Belt drives. Intersection shafts, U joint, hooks joint. If E is equal to 0, flange coupling. Relative sliding velocity is equal to offset distance between shafts into angular velocity of shaft. Oldham coupling is used to connect shafts having small parallel misalignment. Position synthesis of crank rocker mechanism or extreme position of rocker in crank rocker mechanism. Input to output to coupler, LB is equal to circle, LC is equal to arc of circle. This is beta, this is alpha, 360 minus alpha, theta 1, theta 2. Beta is equal to 180 degrees, this position. Beta is equal to 0 degrees, this position. Beta is equal to 0 and beta is equal to 180 degrees, toggle positions. Alpha is equal to 180 plus theta 1 minus theta 2. Gamma is equal to 180 minus theta 1 minus theta 2. Theta is equal to omega t. If omega is equal to constant, theta directly proportional to t. In a crank rocker mechanism, the rocker will be at its extreme position corresponding to toggle. That is when input and coupler are collinear. Since the rocker is oscillating link corresponding to extreme position, angular velocity will be 0. Angular velocity will be 0. Beta, this is beta, this is gamma. Gamma transmission angle in a 4-bar mechanism, it is angle between coupler and output link. Corresponding to large value of gamma, mechanical advantage is more. Corresponding to smaller gamma, it is found that even a smaller amount of friction may lock or jam the mechanism. Extreme values of transmission angle gamma in crank rocker mechanism. In triangle ABD cosine law, k square is equal to a square plus b square, a square plus b square minus 2ab cos theta. In triangle BCD, k square is equal to c square plus d square minus 2cd cos gamma. Equating 1 and 2, c square plus d square minus 2cd cos gamma is equal to a square plus b square minus 2ab cos theta. 2cd cos gamma is equal to c square plus d square minus a square minus b square plus 2ab cos theta. Gamma is equal to f of a comma b comma c comma d and theta constant. Gamma is equal to f of theta. For gamma to be maximum or minimum, d gamma by d theta is equal to 0. 2cd into minus sin gamma d gamma by d theta is equal to 0 minus 2ab sin theta. D gamma by d theta is equal to ab by cd sin theta by sin gamma. D gamma by d theta is equal to 0. Sin theta ab into sin theta by cd into sin gamma is equal to 0. Either ab by cd is equal to 0 or sin, which is not possible, sin theta by sin gamma is equal to 0. Either sin gamma is equal to infinity, not possible, or sin theta is equal to 0. Theta is equal to 0 degrees or 180 degrees, where theta is this angle. Configuration diagrams at theta is equal to 0 degrees, gamma minimum we will get. At theta is equal to 180 degrees triangle, we will get gamma maximum. Cosine law, a minus b whole square is equal to c square plus d square minus 2cd cos gamma minimum. A plus b whole square, here a plus b whole square is equal to c square plus d square minus 2cd cos gamma max. Cos gamma max. From this we can get gamma min and gamma max. Mechanical advantage, MA is equal to torque at the output by torque at input. It is defined as ratio of torque at output to the torque at input. Mechanical advantage indicate the quality, that is effectiveness of any mechanism. Efficiency of mechanism is equal to power at output by power at input. Eta is equal to T output omega output by T input omega input. If there is no loss in power due to friction, then power at output is equal to power at input. T out omega out is equal to T in omega in. T out by T in is equal to omega in by omega out. So mechanical advantage is equal to T out by T in is equal to omega in by omega out. Omega in by omega out. Velocity ratio Vr or lambda. Velocity ratio is equal to omega out by omega in less than 1. Mechanical advantage is equal to 1 by Vr. Vr denote the effectiveness of those mechanisms which can transfer relative motion without transformation. Example, gear and pinion, belt drive, etc. In 4-bar mechanism, mechanical advantage is equal to sin gamma by sin beta. Gamma transmission angle between coupler and output link. Beta angle between input and coupler. The transmission angle gamma and angle beta depends upon the link which has been chosen as input. Therefore mechanical advantage will also be defined relative to the input and output link. Since the angle beta and gamma changes continuously, mechanical advantage will also change continuously at toggle position, that is when input and output link are collinear. Beta is equal to 0 degrees or 180 degrees. Beta is equal to 0 degrees or 180 degrees, that is between input and coupler. And then mechanical advantage is equal to infinity. The infinite value of mechanical advantage means very large output torque can overcome by small input torque. Beta is in between input link. Beta is between input link and coupler. When it is like this, toggle position, theta is equal to the beta is equal to 0 degrees or 180 degrees. The infinite value of mechanical advantage means a very large output torque can be overcome by very small input torque. For mechanisms which are used to raise load for them, mechanical advantage is equal to load by effort. Example, screw jack, mechanical advantage should be greater than 1. X is equal to 1 minus cos theta into OA. Graph. Subject to question on mechanical advantage. Quick return mechanism QRM. The mechanisms in which return stroke consumes less time than cutting stroke or a forward stroke is known as quick return mechanism. QRR, time required by driving crank from during cutting or forward stroke by time required by driving crank during return stroke. QRR is equal to T cutting by T return. Theta is equal to omega T. If omega is equal to constant, theta directly proportional to T. Theta cutting by theta return is equal to T cutting by T return. QRR is equal to angle turned by driving crank during cutting stroke by angle turned by driving crank during return stroke is equal to alpha by beta greater than 1. Performance of any machine directly proportional to number of parts manufactured per unit time. Performance inversely proportional to cycle time. Forward, it has forward and return. If QRR is less than 1, QRR is equal to beta by alpha. Offset slider crank QRM. Configuration diagram EGOAB RL pi E, either like this or like this, like it is above, E is more, E is less, or E it can be below. To calculate QRM with QRR stroke length and stroke length, first we need to calculate extreme values. That is, if it is at extreme position, these extreme positions pi, that means this angle is 0 and 180 degrees. When pi is equal to 180 degrees, it is like this. When pi is equal to 0 degrees, it is like this. Theta 1, this is theta 1, this is theta 2. The angle between this is theta 1 minus theta 2. R is equal to crank radius, L is equal to length of connecting rod, E is equal to eccentricity. When pi is equal to 0 degrees, this is E, total L R theta 1. Sin theta 1 is equal to E by L minus R hypotenuse. Cos theta 1 is equal to OC 1 by L minus R. Sin theta 2 is equal to E by L plus R, and pi is equal to 180 degrees. Cos theta 2 is equal to OC 2 by L plus R. Stroke length is equal to B1 B2 is equal to C1 C2 is equal to OC2 minus OC1. B1 B2 is equal to L plus R cos theta 2 minus L minus R sin cos theta 1. QRR is equal to alpha by beta. Alpha plus beta is equal to 360 degrees. Alpha is equal to 180 plus theta 1 minus theta 2. 180 plus theta 1 minus theta 2. Beta is equal to 180 minus theta 1 minus theta 2. QRR is equal to alpha by beta is equal to 180 plus theta 1 minus theta 2 by 180 minus theta 1 minus theta 2 greater than 1. If less than 1, then QR is equal to beta by alpha. Next, crank and slotted bar. Crank and slotted bar QRM, quick return motion crank rocker, in which connecting rod is fixed. This slotted crank and slotted bar, it will be like this tool. This will be connected to a tool or the 6-bar mechanism, inversion of single slider mechanism, crank rocker mechanism. In reality, tool movement will is horizontal always, that is straight line. Number of links is equal to 6, number of revolute pairs is equal to 5. LB arc of circle, center O4, center of rotation of link 4, that is slotted bar, radius O4B is equal to length of slotted bar, center O2, center of rotation of crank, radius O2A, crank radius. Although R1, R2 and B1, B2 looks like arc in arc, it is a straight line. Note, V slider or slotted bar will be along the slotted bar. Tool will be at extreme position when slotted bar is at its extreme position, and the slotted bar will be at extreme position when it is perpendicular to crank. That is at A1 and A2. A1 and A2, this OA will be perpendicular to this slotted bar extremes of circle. Since slotted bar is oscillating link at extreme position, its angular velocity will be 0. The, this is fixed link A1 A2, here perpendicular, here also perpendicular, O2 O2 O4, A1 A2, B1 B2. This is forward. This is beta. This is for alpha. Alpha plus beta is equal to 360 degrees. In triangle O2 O4 A1, cos beta by 2 is equal to O2 A1 by O2 O2 A1 O2 A1 by O2 A4. O2 A4, as this is hypotenuse. Cos beta by 2 is equal to driving crank radius by fixed link radius. QRR is equal to alpha by beta is equal to 360 minus beta by beta. Observation: if crank radius is equal to half fixed link, cos beta by 2 is equal to half, beta by 2 is equal to 60 degrees, beta is equal to 120 degrees, alpha is equal to 240 degrees. Cutting stroke QRR is equal to 2:1, if greater than 1 is 1:2, if all less than 1. Reverse is also true. For example, QRR is equal to 1:2 given beta by alpha is equal to half, alpha is equal to 2 beta, alpha plus beta is equal to 360 degrees, beta 3 beta is equal to 360 degrees, beta is equal to 120 degrees, beta by 2 is equal to 60 degrees, cos 60 degrees is equal to half is equal to crank radius by fixed length. Stroke length. The tool is constrained to move in a straight line. Therefore, stroke length is equal to R1 R2 is equal to B1 B2 is equal to B1P plus B2P is equal to 2B1P is equal to 2O4B1 sine of 90 minus B by 2. Stroke length is equal to 2O4B1 cos beta by 2. 2O4B1 cos beta by 2. 2O4B1 cos beta by 2. Okay. Stroke length is equal to 2 into length of slotted bar into crank radius by fixed link length. 2O4B1 is slotted link length, cos beta by 2 is crank radius by fixed link. Observation: the velocity of tool will be maximum at midpoint of stroke and mid of stroke, and corresponding to it fixed link crank and slotted bar will be collinear at this point at O2 for this point. Stroke length: the tool is constrained to move in a straight line. Therefore, stroke length R1 R2 is equal to, okay, this thing we already did. Observation: okay, collinear. Omega slotted bar will be maximum at ESE during cutting stroke. Omega slotted bar will be minimum at AR during return stroke. Omega slotted bar at AR return greater than omega slotted bar at AC. V slider or slotted bar at AC and AR is 0. V slider relative to slotted bar at AC and AR is equal to 0. A Coriolis component acceleration A Coriolis is equal to 2 V slider relative to slotted bar into omega slotted bar. In one cycle, Coriolis component is 0 at 4 times. At A1 and A2, omega slotted bar is 0. AC and AR, V slider bar relative to slotted bar is 0. Here A1, A2. Here V slider, AC and AR, it is again 0 when it passes through midpoint. Whitworth QRM. This shall be circle center O4, radius O4B, LA circle center O2, radius O2A. 6-bar linkage, crank mechanism, inversion of single slider mechanism. Tool will be connected here. R1 R2 is equal to B1 B2. Hint: point A O4 B and B will always be collinear. Point B and R will always be collinear. Alpha plus beta is equal to 180 degrees. A1 A2. Cos beta by 2 is equal to O2 O4 by O2 A1. Cos beta by 2 is equal to fixed link length by driving crank radius. O2 A1 is driving crank radius. QRR is equal to alpha by beta is equal to 360 minus beta by beta. Stroke length is equal to R1 R2 is equal to O4 R2 minus O4 R1 is equal to O4 B2 plus B2 R2 minus B1 R1 minus B1 O4. O4 is equal to O4 B1 is equal to O4 B2 and BR is equal to B1 R1 is equal to B2 R2 is equal to O4 plus BR minus BR plus O4B. Stroke length is equal to 2 O4B is equal to B1 B2. In a crank and slotted bar QRM, the stroke length depends on 3 different links, whereas with QRM, a stroke length depends only on one link. Therefore, in crank and slotted bar, there is better control of stroke length than Whitworth QRM. Hence, crank and slotted bar is more useful. These are just workbook questions.